You can see my screen?
Yes.
Okay. So, good morning, everyone. Welcome to this Generative AI for Managers program. Um, so, this is uh, primarily meant for those people who are somewhat technical, but also non-technical, and try to make sense of the landscape of generative AI, right? I'm sure you would have already gone through the course outline that I have shared earlier, right? And the core objective of the course is to go through the important aspects which will actually empower a manager to kind of understand the landscape of generative AI, um, along with some basic technical foundation of generative AI, but also understand who are the key players, what are the tools and platforms and frameworks people use to develop generative AI solutions. So we'll go through that in quite detail. In the meantime, also we'll look at what are the different applications or use cases that you can actually develop using generative AI, right? What are the people and look at some of the case studies, how people, organizations are leveraging generative AI, and over a period of time, what are their learnings, right? What are the guidelines and what are the best practices, right? So far, of course, it keeps changing. As you know, the whole field of generative AI is evolving, right? So, so still, but what are the guidelines and best practices uh, from their learnings that we will look into that. And we'll also look at the practical consideration for the managers. For example, they have to start a generative AI project, what aspects they should look into, right? In terms of skills, in terms of people, in terms of platforms, right? What they should adopt. So, end of this particular workshop, you should be able to familiar with all these different aspects of generative AI, and you should be able to talk to the customers, right? Make sense of what people are saying, right? And also keep track of the new advancements in the field of generative AI. Um, I have already shared the session schedule. This is going to be on the Saturdays, starting from today, the 4 Saturdays, same time, 8 to 11 a.m. Indian Standard Time. And the sessions will be recorded. In case you cannot attend the session, the recordings will be shared. So ensure that you go through the recordings before you come to the next session. There might be some assignments starting from second session onwards, just to explore and understand. So we'll talk about that when we come to that particular point. Um, the participants, of course, need to sign up for the OpenAI ChatGPT. If you don't sign up, also the free one is okay. But if you sign up, probably will take more advantage. I will demo it anyway. And some basic requisites and house rules. I assume that most of you would have already gone through the basics of ML, so you understand the basic concepts of machine learning. If you don't understand some of the concepts need to be elaborated, please let me know, um, so that I can actually touch upon those concepts very at a very high level, of course, because this is not an ML session, so that you know understand what I'm talking about in this particular workshop. The sessions are designed to be a question answer mode. So we have Atma here who is going to moderate um, you know the sessions. So if you look at the brochure also, right, there are a lot of these questions. There were 30 questions which has to be, we have to go through each one of them. And of course, there are some more questions that will come up in the meantime, right? So Atma is going to ask a question, and I'm going to answer that. And while answering, I'll go to the relevant topics. So go to the slides and explain that. So each topic may take about, guys, you're not able to hear anything?
We can hear you.
Okay.
You are
So,
audible.
okay. So each topic will take about 15-20 minutes. Okay. So to not break the flow, I would say if you have any question, put in the chat window. The Atma is going to moderate that. But at the end of every 15-20 minutes, I'll open up for 5 minutes for questions so that we can discuss that. Right. Uh, uh, Avoid optimizing it early. So at least the first two sessions, don't think about the problem that you have at your hand that you want to solve it, right? And ask, how do I solve this problem? Let's first make sense of the complete landscape, right? Of course, when you come to third and fourth session, when you talk more deeply into the different use cases and case studies, maybe you can go, we'll allocate specific time if you have anything in mind and how do we actually do that. So the first two sessions are mostly, of course, you can ask questions, but do not only think about your specific problem. All right, we'll generally talk about the use cases and all that. Okay, so these are the house rules. Try to avoid any distractions this in 3 hours. All right, keep focus, and let's take benefit from this workshop. Yeah, any before I start, right? This is also getting recorded. Yeah. Correct. Okay. So we will start with the first, Atma, can you go ahead?
So the first question is, how is generative AI different compared to traditional AI? Can you explain with an example?
Okay. So I think that's an important, uh, you know, point to start with, right? I think some of you or most of you will have already, understanding of the traditional AI. So what I'll do is, I will take a use case or a case study. How would you actually solve that using traditional AI? And how would you actually solve using generative AI, right? And how it is different and what advantage and benefit that it has over the traditional AI may not be applicable to all kind of problems. We'll also discuss later which specific problems you will not apply generative AI as well, right? You'll still stick to the normal traditional AI. Okay. So for this example, I've taken a very simple yet complex. You will discover that it's quite a complex implementation, right? Let's say there is a restaurant which wants to do a customer experience analysis, right? Try to understand how the customers feel about their food or services, right? So that they can actually do a customer engagement, right? Or they can improve upon certain aspects of their service, right? Based on the customer's feedback. Now, one of the way to do that is basically tap into customer reviews. Either they can do a direct survey. They ask customers to fill the survey. Typically, what you do at the end of um, uh, we eat our food, right? They ask you to kind of fill the feedback forms, or you can actually tap into different social media channels where they can actually look into the reviews. So if you look at the reviews, there will be some examples are here. There'll be kind of mix of reviews, right? Some people are extremely happy about every aspect of the restaurant, like a food quality, customer service, and all that. Some people probably, are only happy about certain things about the restaurant, but not very happy about other things, right? So you can see, we've taken one example here, right? Um, so the food quality you look at the food quality was really good. Um, so I wanted to order more, but honestly, the place did not feel the clean, right? So they're actually happy about the food quality, but not very happy about the ambience or the hygiene factor, right? The service was fine and nothing special. So not very happy, positive or negative, probably were quite neutral. But if you look at here, the waiter had a serious attitude and had to wait forever to get the check, right? Probably food was very good, but not happy about the customer service. Now, um, a lot of organizations, what they do is they do something called aspect-based sentiment analysis, right? So rather than looking at the overall sentiment of the review, they look at different aspects. All will be ingrained into a single review, right? So, for example, the organizations say, okay, we need to look at these different aspects. So these aspects are predefined probably, or they can evolve over a period of time. They do something like a topic modeling and find out what aspects customers are talking about, depending on the business. For example, let's say three different factors here they are looking at. One is food quality. So, and these factors are something that they can actually control, right? And monitor individually. Then there's ambience and hygiene, and then there's customer service. And all of different aspects can have a mix of positive and negative sentiment, right? And how these reviews are going to help, they do sentiment analysis across different aspects, right? One is they can actually help them to engage with customers, right? They can acknowledge and negative feedbacks can be resolved proactively. And they can also prioritize improvements, right? If one aspect of the restaurant gets a consistent negative review, they can actually, prioritize to improve upon that, which will overall improve customer satisfaction and react quickly to issues. And extremely negative, reviews, they can immediately respond to that to improvise them. For example, the ambience or hygiene factors. Now, how typically people would approach to solve this problem, right? Um, if you look at over a period of time, people started with a manual review, but they had moved on to something like ML-based sentiment analysis, and now generative AI, right? So we will go through each step and see what advantage generative AI has given, right? Uh, Typically, manual is either you can have a person, typically we call them annotators or reviewers, who will actually go through these reviews, manually and independently, and log into a system saying that this review is about this particular aspect and this positive or negative, right? And there are also people have used something called rule-based or expert systems, right? So rule-based expert systems are something like rules are explicitly programmed into the systems, right? So this is, of course, very old now. Still, people use a lot of these systems in different use cases. A lot of organizations, the decision-making systems are typically run yet still based on the rules. So there are experts who have understood the businesses very nicely, and based on the intuition, their understanding, they would have explicitly dictate these rules, and these rules should be explicitly programmed into the systems. Typically, if you know, like if-else conditions, right? And very popular, especially industries like finance or insurance and all that. For example, one example is fraud detection system, right? So uh, the experts would come out with something like static rules or velocity rules. Static rules are like, which are if a particular user belongs to one country and the card is used in another country, right? Typically, it's a flag, right? But velocity rules also based on the behavior, which keeps on changing. For example, they look at how much the customer is spending in last 3 to 6 months, what's an average spending. So there'll be a distribution of spending. And then all of a sudden, the spending goes much beyond that, like an outlier or an anomaly, right? Then also it actually raises a flag. So these are basically certain rules the experts would dictate, and that will come into if else rules. The only problem with this kind of systems, and especially if you do for sentiment analysis, right? So they would look for specific terms and phrases, right? They'll do a string search or regular expressions and they find out the particular terms and phrases are there, then it's a positive or then also negative, right? They look for specific phrases in those sentences. But they're very quite complex. And one of the drawback of these expert systems are, you know, uh, they are non-adapting into those. That means they cannot adapt to changes very rapidly, especially in uh, in cases like fraud detection, where the fraud patterns keep changing, and also even in the sentiment analysis, also the way people express also keeps changing over time, right? And can be a mix of languages. Sometimes people use multiple different languages, English along with something else, right? It's very complex to kind of write those into the rules. So they are very slow to adapt to changes and very complex also. Over a period of time, you will start writing hundreds of rules and becomes completely unmanageable over a period of time. So people have moved on to something like ML systems, right? And how ML systems work is you have a historical data. So you have a set of reviews, right? And you have already kind of collected saying they are positive or negative, right? And then you run through an algorithm, typically like your machine learning, deep learning, or statistical learning algorithms, which will actually spit out a model, right? So your data is your input, and your process of learning is basically your algorithms, right? For example, you might have worked on algorithms like decision tree classifiers, right, or random forest classifiers, or logistic regression, or linear regression. These are different algorithms, right? And these algorithms will spit out a model. A model is nothing but a representation of the pattern, right? It will basically say, okay, if this particular term is there or phrases is there in that particular sentence, the probability of this being positive is high, the probability of this being negative is very high. So it'll basically come up like a naive-based classifier just to tell that, right? What is the probability that the sentence is a positive sentiment given there is a word called fantastic, right there. So it comes with this like you know prior probabilities, right? And it estimates these probabilities for across different words, okay, given that their presence is a positive or negative sentiment, and then basically accumulate across different words and estimate the total probability at the end. So the whole idea is you have input data which are reviews or samples of positive negative. You run through the algorithm and basically create a model, okay? And what happens is you can always retrain these models the newer data and keep learning, so the adapting to the changes is very fast, right? And because the mathematical expressions formula or statistical learning, it can actually also incorporate very complex algorithms, okay, very complex patterns, unlike typical if else rules that we use in the traditional systems. So if you look at the whole process itself is it's very complex, right? For example, you always have to start with the level data, right? You may not have a level data. You all that you have is a reviews. So what you do is you have to hire certain annotators or data labelers. In fact, if you look at the whole ML and even the generative AI, we also need annotators. I'll tell you that later how and why. You always have to be annotators or data labelers who are domain experts, right? Who understand the domain. For example, if you want to label a data in a finance domain or a legal, then you have to have annotators who understand that particular domain very well, right? So they go through manually these reviews and then label them saying that this particular review is positive, this particular review is negative or neutral, and so on and so forth, right? And believe me, this is a very time consuming and very expensive step of building machine learning models or AI models. And once they have gathered a label data, then of course For example, if you see here, there are a lot of these reviews which are have positive and negative sentiments, right? It's already labeled by the labelers. And you take randomly a part of the data as a training and part of the data as a test set to evaluate the model. And then you go through this traditional process of model building, right? So you have a labeled data now, which is created, annotated by the labelers. Sometimes, of course, this data will not be labeled by the annotators. This would be system generated. For example, fraud detection systems are kind of a hybrid. Some of them are actually generated by the systems, and some of them are actually annotated by the system itself. For example, if a transaction goes through as a non-fraud transaction, and the customer finds out there's a fraud in the account, so you will always have at this time period of 48 hours to report to the bank that this transaction is not done by you. It seems like a fraud, so they basically flag it, right? So there's always a annotators or customer support involved in flagging those transactions, right? Or if it blocks a transaction like a fraud, if you would have observed, sometimes you get a call from the bank saying that, are you doing this transaction? Right? So they block it first, then call you, and they say, yeah, I'm doing this transaction. Then they basically go back and uh, unblock the transaction. So that also creates a label data, right? So sometimes it's completely manually labeled, and sometimes it's actually system generated, right? And then of course you have a training data and test data that you create out of the level data, and these data are basically version controlled because the models are extremely tightly linked to this data. Then from this training data you actually train a model, right, which learns from the data, okay, um, you know uh, to predict if it's a fraud, non-fraud. In this case, of course, a positive or negative. And then with the test data, you evaluate the model, okay? And the evaluation accuracy is correct. I mean, the expected accuracy or metrics. We'll go to some of the metrics for some of the generative AI use cases later. You keep on retraining until your evaluation metrics are as expected. Then, of course, you deploy the model. And these are the new reviews that's coming in for the customer. And then you predict that as a positive or negative feedback, right? So this is a typical process that you follow in ML. But this is also not as simple as this, because most people just don't look at the whole review and say it is a positive or negative, right? So they actually want a lot of additional information if they can extract, like an aspect-based analysis, right? So is one model enough? Probably not. Because if you look at the whole aspect but sentiment analysis, there are many different things that they do want to do. One is they do something like, you know, term or phrase extraction, right? They want to look at a specific. So when you're talking about hygiene, which hygiene you're talking about? Is it the hygiene of the place they're eating, or you basically the washrooms, or any specific things that you're talking about? Or if you're talking about food quality, the quality of the food, either in terms of again, it's too spicy, or a specific aspect of that. So it's also important that you extract certain terms and phrases from those reviews, right? And some of these terms could be very implicit and some could be explicit. We'll come to some example. You cannot really find out, you know uh, it's not explicitly mentioned in the review. So one is you need to have a model to extract certain terms and phrases from the review. Is anybody still waiting on the? Just wanted to quickly check. Is the audio fine? Everything is okay?
Everything is good.
Yes.
Okay. Then the other one is categorization, right? So once you extract certain terms and phrases, because it's possible that one single sentence contain multiple aspect, or each sentence in the review can be attributed to one aspect, right? So you can also do term categorization. So this is very specific. You're saying, okay, this is about food, about hygiene, or about customer service, or combination of this. Okay. So this is typically we call it a multi-level classification. Okay, multi-level classification in ML. There's something called multi-class classification. So ultimately, the review belongs to a specific category, but it can actually belong to multiple categories simultaneously, right? Um, so categorization, and then of course sentiment. So once you identify, now for food quality, it's a positive or negative. For hygiene, it's a positive or negative, right? So if you see, this is not simply building one model to understand customer is positive about everything or negative everything, but rather than one is information extraction. You are extracting information, but sometimes the information is available implicitly or explicitly. So you have to understand that. Then you categorize that information, whether it's about a specific aspect. And then once you understand the aspect, you also have to classify whether it's a positive or negative about that particular aspect, right? So if you do, for example, what is explicit and implicit? So if you look at particular example here, the aspect is directly mentioned in the text, whereas the aspect is implied or inferred from the text, right? For example, somebody's the food was delicious, but the service was slow. So you know that this talks about food quality and service. But if you see here, I waited over 30 minutes before anyone took my order. So here the service is implicitly implied, right? It's a service. So it's a positive and negative. Again, um, it's delicious and slow are explicitly mentioned, but here it's not really saying that it's positive or negative. That is something that you have to derive from the model. So a keyword based, your traditional um, the rule-based programs probably would fail here, because if they're looking for a specific phrase or term, they will not be able to detect this. So ML model is absolutely necessary to identify this. And one example is like the ambience of the restaurant was great. So it's explicit. The place was too noisy to enjoy the meal. It's quite implicit. And that's also not, so it's not about simply extraction of the terms, then categorization, and then classification. It's also about other aspects. For example, some people sometimes give very toxic and abusive reviews, and you don't probably want to deal with them directly. You have a certain other channels to deal with that, right? For example, the food was probably some expletive words, disgusting, and the service was worse, right? So the people can actually use slur, right, derogatory terms and expletives, right? So you also have to have another model to identify whether we should be even looking at this particular review and responding to the customer directly, right? Or is there another mechanism to deal with this? Probably you will ignore, or probably you will find a different mechanism to deal with that. So you need to also have another model to find out if the review is very toxic or abusive or not. Right? So if you look at overall model, right? You also do have first have to do a toxic classification, right? To find out if it's a toxic or non-toxic. Then aspect extraction, right? A specific terms and phrases, then categorization, and then sentiment analysis, right? So if you look at the sentiment analysis, quite complex, right? And probably you have to build an ML model traditionally for each one of this, because ML models are kind of specialized models, right? So each model comes with a specific, specialization that is basically great. So you have to do, data collection for data toxic classification and build a model separately. You have to do a aspect extraction. You have to do a NER, entity recognition, or phrase extraction kind of model, then multi-level classification, then binomial sentiment classifier, right? So we build four different models, right? Which is not easy. And then once you have done a sentiment analysis, right, of the reviews, you also probably would like to automate, right, the responses to the customer, right? For example, sometimes the customer would require immediate attention to certain reviews. So you write a mail to them. So typically, traditionally, what you do is you use something called canned responses for engagement, right? For example, if you see there is a review that you got right, from the customer. And typically people normally they use something called a template based response. And normally you will see even today 95% of organizations they use canned responses or template based responses. So thank you for your feedback, taking time to share. Your feedback is incredible value to them and the best possible dining experience for all of us. So we look into that. So they are not talking about or they're addressing the specific issue the customer is talking about, right? But now what happens is you can move away from the canned responses and you can also do a personalized response, which is key to engagement. So nowadays, if you look at everything is important for personalization, right? To key to engagement. For example, you can say, "Dear customer, and thank you for sharing experience. We are thrilled to hear that you enjoyed the food, but we are truly sorry the cleanliness did not meet your expectation." Right? You're directly addressing or acknowledging the customer's specific issue or whatever the customer is happy about. So this actually no, improves the engagement of the customers much better compared to your canned responses or template based responses. But now generating these responses is extremely complex in traditional ML mechanism because MLs are typically predictive in nature. They are not more of a generative in nature, right? So personalization is one of the important use cases for generative AI nowadays, right? So if you look at the complete, you know, uh, the overall process of sentiment analysis, it actually involves so many different things. The first step, typically, people also do language identification, like a detection or translation, because multiple languages might be there. Then toxic classification, aspect-based extraction, categorization, sentiment analysis, then personalized responses, right? Email messaging. And developing the systems is not easy, right? Because you have to develop so many different models. You need even a model for translation or a language detection. Yeah. So the next question.
Thank you, Manoranjan. One second. The second question is, how does generative AI approach this specific problem in comparison to traditional AI?
Right. So if I have to go and develop this solution in generative AI, so generative AI has made this extremely simple, right? For example, prompt. And you must have heard about prompt engineering, right? So prompt engineering can actually tackle this problem with a single prompt. So you can write a prompt something like this, you're an advanced sentiment analysis system, and your task is for the customer reviews, right? And you can specifically say that, okay, the you extract sentiment about this particular aspects, food quality, hygiene, and customer support, right? You define what aspect, what sentiment, what keyword means. And most of the times when you write the prompt, you can also define how the output will be given. So the schema definition also can provide in the prompt itself, right? And um, you know, here is basically a response from the prompt from the generative AI. So it takes the review and analyze it. You provide the aspect, provide this positive or negative feedback and some of the keywords, right? And if you see that um, from building so many different models to deal with this has been completely replaced by a single prompt, the generative AI, right? You can also do multiple different tasks. So you can, the same prompt itself can do the toxicity detection, extraction, and sentiment classification, right? So it's all about now, prompt engineering. Of course, there are limitations of prompt engineering. I will come to that point a little later, but you can kind of create a structure around the prompt, basically identify aspects, extract sentiment, keyword, but also flag inappropriate content like a toxic, abusive, or unethical language and all that. Okay, and return the results in a schema, right? So that's basically can be done with the new generative AI models, right? Which can actually do multiple different tasks and uh, kind of, you know, simplify the whole process of building multiple different specialized models with a single generative model. Okay. Um, I think we can open up little question for others. Anybody has a question? Okay. So, Atma, what's the next question?
The next question is there any significant difference in effort in building Gen AI-based solutions compared to traditional AI solutions?
Absolutely. I mean, if you look at the whole ML development itself, the cycle or the effort or the cost needed to develop different models are completely, replaced by using one single generative AI models. So I'll give a simple, demonstration of typical efforts. If you look at traditional ML and GenAI based development, this is only I'm talking about sentiment analysis, right? Normally it takes about, in a thumb rule, right? Typically about 3 to 6 months of effort, right? And majority of the effort actually goes in the data collection and data labeling. Then, of course, model development, and then model evaluation, deployment, and basically ongoing monitoring and all that. So if you look at this effort of training and building the first model and deploying to the production, it takes about 3 to 6 months of effort, depending on the complexity of the project. Sometimes it takes about 12 months as well, right? If you look at building all these models for toxicity detection, phrase extraction, categorization, and classification, all will take about a lot of time. But if you look at now, typically generative AI models, you still need data level data, especially for evaluation. Okay, you simply cannot do prompt engineering because sometimes you also need to understand whether the generative AI model is able to classify or extract terms and phrases based on our need or requirements, right? You still have to, um, you know, evaluate the model's output, right? You may not need a data set for training a model, but you still need an evaluation. So the timeline for that is significantly reduced for, data collection. Probably here, if you need probably 1,000 or 10,000 samples to train a model, this probably you would need about 500 to 1,000 samples just for evaluation. And as far as model development, probably is very little time because most of things will be prompt engineering. Okay, we'll come to fine tuning, which might little require some more time. And then, of course, the remaining time typically remains same. Okay. Deployment is also quite complex in terms of traditional ML because it has to follow a lot of ML ops processes, but this is simply a prompt engineering. So typical time for deployment is also much lesser. Yeah. I think some questions.
We've got the first question from Yashwant, which is how do we do post-deployment monitoring?
Yeah. I think we'll come to that aspect little later, Yaswant. Okay. There is something called a model drift, right? I'll just give a little uh, pretext to that. For example, if you um, whenever you build a ML model, the model is only valid for the distribution of the training data because it's actually trained on the training data. So whatever distribution the training data is, the model is only valid for that. But what happens is over a period of time, the underlying business context changes. So this most of the models, of course, it depends on the domain again. The models typically tend to decay over a period of time. The performance of the models tend to decay. For example, fraud models, typically the models performance decay very fast, very quickly, probably over a few weeks. But the healthcare models typically they don't decay rapidly. They take many years to decay, unless we have a change in lifestyle or whatever, or some new intervention has come which changes the disease patterns and all that. So based on the domain, you have to keep monitoring these models, whether the model has drifted away, right? The accuracy is reduced or the data distribution is reduced. And then, of course, you'll have to come back and recreate or retrain these models. But we'll go to a little more detail later. Okay. Yeah. Any other
So
questions?
a couple of other questions. One is how to select. So first one is from Abhilasha, which is how much data is required for data modeling?
Okay. So this is for traditional ML if you're talking about how much data is required. The typically the number of samples that we need based on the complexity of the business case. For example, one of the complexity factor is the number of features we have. Right. For example, if you're trying to detect a transaction as a fraud or non-fraud, you will have certain factors like what's the transaction amount, what's the product the customer is buying, when is buying, what is the moving average of the customer spending pattern in the last 3 weeks, right? So these are different features. And these features typically um, will dictate the complexity of the model. So normally about 50 to 60 times, right? You will need that.
He
Um,
says no for Gen AI, he's asking.
you're saying how much data is required for GenAI models?
Yes, that
Okay.
seems to.
So typically for prompt engineering, of course, you don't need data, but evaluation, you will need that. But there's something called also fine tuning. I'll come to that. Okay. Some of the questions will be addressed in due course of time. So please wait for that. Yeah. What's the other question?
Uh, the next question is how to select the Gen AI model which is best of particular use case from
Interesting.
Atul.
Oh,
And I thought maybe there's some confusion in the data modeling with the new AI models, the Gen AI models, that these actually contain within the model a huge amount of data modeling over public data. And so we're generalizing over that. That may be something that needs to be uh, highlighted as well. So
yeah.
where the data is coming from as well.
Yeah. I'll talk about that. So first we'll look at now how these generative AI models are built. Okay. And if you're looking for a specific use case and all that, how you have to look at how which data is trained on, all that you look at that. Okay. And there's one more question from Abhilasa. What is that?
The question is, you mentioned about prompt engineering. There is a RAG technique. RAG stands for Retrieval Augmented Generation.
Hmm.
When to use prompt and when to use RAG,
Very interesting.
how it will impact the timeline.
Okay. Again, we'll come back to that when we talk about RAG. Specifically, we'll talk about RAG in the third session, or probably second session towards, we'll address that as well. So some of the questions will be addressed. I think we're just starting no, now. So we will keep track of these questions. We'll answer them in the due course of time. Okay. Okay. So what's our next question to
The
discuss?
next question is how does one generative AI model learn to accomplish so many different tasks?
Yeah, that's very interesting aspect, right? So um, we were developing ML models as specialized models for specific tasks over a period of time, and how generative AI is able to do so many different tasks, right? So I think the turning point happened somewhere in 2019 when OpenAI released this paper or publication saying that the language models, right, are unsupervised multitask learners. So they told that you don't have to train these models for specific tasks because especially when you're talking about the language understanding, right, all these tasks have a very common aspect. Okay, so if you're training a model on the typical languages, right, so they're capable of doing multiple different tasks. And before this, if you look at for NLP, people were building different kinds of models. And if you look at there is a Hugging Face model hub there. Okay, this is one of the public repositories where people build either specialized models or generative generalized models and then upload it Typically, it's a repo of um, open source models, right? And if you look at natural language processing, okay, if you look at the models, and you can see there are different kind of tasks, and for each task there are a set of models. So this was the trend earlier, like a text classification, token classification, which is like NER, right? Identify it's a name or location or geography or whatever. Like in case of review, if this particular phrase or term is about food quality or customer service and all that, right? Or question answering, translation, summarization, right? Sentence similarity. If you look at people who are actually developing specialized models for specialized tasks, right? But then they came and told you don't have to do that. The model can be um, built for multiple different tasks. And to understand how these models are multitask learners, right? We have to dive little deeper into how these models are actually built. So today we'll spend some time in understanding how these models are typically built. And in the process also we'll understand certain aspects of these models, and which will be very useful when we're talking about building solutions, right? In fact, there is not one single model. Even today, there are a couple of different types of models out there, right? So first question that you can ask is, you know, how do even computers understand the words and sentences? All right. um, so if you work on generative AI and building solutions on generative AI, you must be very, very familiar with this idea called embeddings, or we also call it the numerical representation, right? Numerical representation of words or sentences, right? By the way, you can also see what I'm writing, annotating on the screen.
Yes, yes, can see.
Okay, thank you.
Yeah.
Just to get an understanding of what exactly is embedding, because a lot of these solutions, right, even RAG or search-based solutions and all that, the embeddings are extremely important concept. So what exactly is embedding, which is one of the foundational block of generative AI models. Now let's say, of course, computers do not understand words and sentences. Computers understand only numbers, all right? So we have to find a mechanism to represent these words or sentences into numbers. But then it cannot be any random numbers. So the numbers have to have some semantics built into it, right? For example, let's say if I say, how do I represent a role called CEO or a CFO or a CTO and all that, right? So there are different roles. Now, how do I tell computer what those roles are, right? One way of course, doing that is something called, we traditionally use something called one hot encoding, right? One hot encoding is one of the traditional, and still people use an ML world representation, is we create a variable called CEO, CFO, or CTO, and all that. If a person is CEO, we say he's a CEO, not a CFO, not a CTO, right? So this is a representation in the traditional world saying that, one hot encoding. Or if a particular person is a CFO, we'll say, okay, not a CEO, but a CFO and CTO. So the person we represent in computer, right, saying 100 or 010, right? This is one, it's called one hot encoding or dummy variable representation. But if you look at this actually 100 or 010 does not contain any semantics in it, right? It's just a way of representing those roles or words into numbers, but does not mean anything. Okay, so they lose complete semantics. Okay, so that become a challenge. So the other way is you can do it is each role you can decompose them into certain attributes and features of that role. For example, all these roles will have some amount of what? Leadership, some amount of technical expertise, financial acumen, operational efficiency, right? All these different, let's say, this is, of course, you're doing explicitly. It will not be possible to do explicitly for everything. We'll come to that. But to understand the concept, let's do it. And then we say, okay, on a scale of 0 to 1, on a leadership, probably CEO is 0.9. Technical expert is probably not much required, right? Financial acumen is definitely yes. The strategic planning is yes, but maybe not so much on operational efficiency and all that. But if you look at CFO, it's more on financial acumen compared to technical expertise and so on and so forth. Okay. So then what you do is when you say CEO, right? And you say, okay, the CEO is actually represented by this bunch of numbers. Okay. And this is basically called a vector representation. Okay. It's called a vector representation of the term called what? CEO. And this is also called embedding of CEO. Right? So instead of saying CEO 011, basically say, if this is the number, okay, this must be the CEO. So computers understand how to differentiate between these words in terms of their expertise. Okay, so this is called embeddings. So for us, now can we go and represent all words, all possible words in embeddings or a set of vectors, right? Which is a very mammoth task, because the number of possible words there in the world are probably millions, right? And we cannot decompose each word into certain aspects or features. We don't even know. Okay, so then what comes is, if you can in a way learn these embeddings through some mechanism, right? For example, if you find a mechanism and learn these embeddings into something called latent factors. Okay, latent factors. That means, let's say we have this 4 words: man, woman, king, and queen, right? And through some mechanism, through some learning process, we found that the man can be represented by this bunch of numbers. The woman can be represented by this bunch of numbers, right? And so on and so forth. And what this each number represent, we don't know. These are latent factors. So this, let's call it x1 or x2 and so on and so forth, right? But then how do you know what about the numbers that is actually represented is correct or not? Okay, so how do you know this vector truly represent man and this vector represent woman? Because we don't know what actually they mean. Okay, and what are this basically the weights? Then there is a concept called word analogy hypothesis, right? There are two different word similarity hypothesis and word analysis hypothesis. So if you take these numbers, ultimately these are vectors only, right? And if you can do some basic algebraic operations, for example, if you do something like this, if you take the vector of king minus the vector of men plus the vector of what? Woman, you can do a basic arithmetic operations, but vector operations. And if it approximates the vector of queen, then we know that whatever representation is done here, they must be correct, right? So we actually build certain hypothesis and saying that if those hypotheses hold true, then the representation might be correct, right? For example, one of the other hypothesis, if you say India, right, minus Delhi, okay, it should be equal to France minus Paris, right? So the distance between the vector between India and Delhi, a country and capital, is very similar. Then we must know that, okay, whatever the numbers that the model is generating to represent those words, they must be correct, right? So this is called word analogy hypothesis. There is also something called word similarity hypothesis. Word similarity hypothesis. What is that? You would take a bunch of numbers and you cluster them, right? If you cluster them, right, and you see the words which are closer to each other, they belong to certain domain, and the closer to each other, for example, all the animals, right? The embeddings are closer to each other, then you know that okay, they're probably right representation. Or the countries are represented together, right? All the medical terms, healthcare terms are clubbed together, right? So then we know that the similar words are nearest to each other because whatever numbers are getting generated, right? So they must be truly representing their semantics, right? So this is how actually we convert the words into numbers. But how do they do it actually? So that's an important algorithm. Just a high level, of course, we'll not go into technical detail. So what they do is they take a very sentences or paragraphs from the web. For example, you can go to Wikipedia, right? Wikipedia is an amazing, repository of very formal text. So you take a sentence and then you build a model saying that if I give the prior words, right, can you predict what is the next word, right? So what they do is basically kind of Windows slide it so that they take these two particular words and predict the next word, then take these two words, predict the next word, and so on and so forth, right? So they create a training data like this. Okay, they actually use a technique called negative sampling, but it's not required. Just understand the basic concept here is take the prior words, not necessarily only two words. It can be much more than that, like 5 words or 10 words, whatever prior, and predict the next what the possible next word is. And you create this millions of samples from the text data and then train a model. And when you train the model, if the model is able to correctly predict the next word, right, then it's possible that the model has understood the actual semantics of this particular words. There is a saying called, the words are known by the company they keep, right? So typically the words are typically known from the context of the words in which they are being used, right? So to understand the meaning of a particular word, if you look at the neighboring words and you understand them, right, then you should be able to predict what the next word is. In fact, all the generative AI models, the foundation again is, it's all about predicting what is the next word or the token, right? So they actually build on the concept of what is the word at the location t based on the function of what is the word at location t minus 1, t minus 2, t means basically the location, up to t minus n. Okay, n could be 5, 6, or 10. Okay. Yeah. We'll come to that. So then how they actually do it is little bit technical, but again, I'll keep it as simple as possible. What they do is first they take all possible words. So all possible words are called vocabulary, right? All possible words. And they represent them into some embedding space. Let's say these are 1, 2, 3, 4, 4 dimension space, right? And what they do is initially they randomly initialize it because initially you don't know what that word's meaning is, right? So simply randomly they can take some numbers here. Okay, these are the numbers which represents the word called thou. These are the numbers that represent salt, and so on and so forth, right? And what they do is now they take two words, the embedding of the two words, and try to predict the next word, right? If the numbers are not truly representing, the probably they'll say, okay, this is the next word, right? Not this, this is the next word. Probably the predicted probability will be 0.9. He's saying that the model says that given this is the prior words, this is the next one. Okay. So this results in an error. Then that result in error will actually, there's a process of back propagation through which they'll adjust these numbers. Okay. Um, Actually, I have a complete video I will like just share with you, which goes to much more technical detail or implementation. But this is being a generative AI for manager program. I'm just trying to keep it at a high level. But if you want to dive into the implementation of this also, you can look into that. But I'll just try to, explain it very intuitively. So they adjust these numbers. Let's say once adjust the numbers, they try to predict again. Let's say in this time, this probability comes down 0 0.8 and this probably becomes 0.1. Okay. Still, it says this is the next word. So in the whole process of back propagation and forward, they keep adjusting these numbers, right? Until there is a point where all the correct words or most of the words are predicted accurately. So there'll be a point of time where we'll actually say this is the next one, right? So they keep on training these models, in billions of iterations, right? We'll look at the compute required for all this, billions of iterations until they actually come to a point where they will predict the all possible next words, right? So at that point of time, whatever numbers are here, so whatever numbers are, it has converged into, okay, that is taken as the true semantic representation for this particular word. Whatever numbers it has converged into, thus which is taken as the final representation for these words. Okay, that's why basically we generate the numbers. And the neural networks, which is deep learning, core of deep learning, is actually the algorithm, right? Which is the core of this algorithm, which actually comprises something called the neurons. Okay, and there'll be an input layer. For example, you can imagine like, give me a second. You can imagine like this is the word embeddings that you are actually feeding to the input neuron. These are the hidden layers with the neurons, and this is the output layer, which basically says what is the next word prediction, right? And um, and these are the connections which are basically called weights, okay, or parameters, right? So if you heard about the models within 1 billion parameter model or 10 billion parameter model, right, or 100 billion parameter model, so the number of parameters is talking about the connections, the weights, okay. So if you see here with just a two layers or three layers here, two hidden layer and one output layer, and each layer containing only four neurons, the number of connections are quite large, right? So if you take like thousands or hundred thousands or millions of neurons, the number of connections will increase exponentially, right? And the number of connections are typically as the number of parameters you have. So when you say 10 billion parameter model, you can imagine how many number of neurons would be there, how many connections would be there, okay? Barring, of course, the other layers like embedding, retention, and all that. So I'll just stop it here for a minute and ask if there are any questions out there. Are there any questions?
We have two new questions from Abhilasha, which is when taking a prior word and predicting the next word, is this the same as transformer?
Yeah. So that's basically a task for taking a prior word and predict the next word. The model architecture is mostly a transformer model. Yeah. That we use currently. We'll come to that little bit, a couple of slides later. We'll talk about what exactly is that. Yeah.
And Abhilasha's second question is, so the weights in the deep learning is only between input and one hidden layer.
The subsequent hidden layer. Okay. So the way the connections are established is a neuron, right, in the previous layer is always connected to the next layer. They don't skip it typically. Okay. So one neuron in the previous layer is connected to all the neurons in the next layer. Right. Again, this will connect to the next layer. So typically that's how the connections are established. Right. And each connection represents one parameter. All right. And this parameter is nothing but weights which are randomly initialized initially. Okay. And through backpropagation, they are adjusted until this model has learned. Okay. So given a word t minus 1 and what t minus 2, if you can predict the next word wt with highest probability, then whatever you have learned, these parameters are freezed. The model is established, right? And that model we use for subsequent predictions and all that.
So I think perhaps what he's asking is if there's only one layer, because he says and one hidden layer, but so do you want to address that about the number of layers in the different models?
Okay. So the number of layers are basically a hyperparameter. So number of layers are not, so typically there are three types of layers. One is the input layer, and of course one is the output layer. So input and output layer will always be one, and one input and one output, but there can be multiple different hidden layers. So number of hidden layers could actually differ based on the complexity of the model. Okay. And the number of neurons in each layer will also differ. So they are typically called hyperparameters. Okay. And depending on the complexity of the model. So nowadays, of course, these are quite standardized in the transformer architecture, how many layers and all that. But yeah, you don't have to have only two hidden layers. There could be multiple hidden layers. And that's basically a variable. And number of neurons in the hidden layer also differs. Okay, so next come to too many words to learn. For example, if you look at any particular language, the possible words are, see the reason I'm explaining this is so that you can actually understand the generative AI. When you're talking about 1 billion parameter model. So you have some intuition around what exactly that billion parameter means. It especially means the number of connections, right, in those networks. And of course, typically the more number of parameters, typically the model tend to learn better. I'll come to that point again a little later. So the next question is too many words to learn. So if you look at any particular language, right, there could be, 100,000 possible words. And if you look at the English itself, there are probably, a million possible words. This also includes the nouns, the location names, the person names, or the product names, organization names. These are also particular words, right? Um, so it's very hard to learn, on the embeddings for all these words. So instead, what they do is, rather than learning the embeddings at the word layer, they decompose the word into something called subwords, subword tokenization, right? Which makes the vocabulary much smaller. For example, if you take a particular verb, let's say play, right? There could be many possible words, right? You can say playing, you can also say played, right? You can also playful, right? They're all possible words. So if you learn independently what they mean, the vocabulary becomes extremely large and too many embeddings to learn from. So rather than you can actually decompose them into something like a play, and there's something called ing, which can be reused across multiple verbs. There's something called ed, there's something called ful, right? So decompose that into tokens. But these tokens are not something that you manually define it. There is an algorithm which automatically learns. Looks at the corpus or the text, right? Whatever the total text that you have, it try to learn what are the possible subwords in that text and creates its own vocabulary. And the vocabulary typically contains the subwords. The typical number of subwords is somewhere between 30,000, right, to about 100,000. So within that, you can actually recreate any possible words in the world, right? Most of them. So for example, if you give an input something like this, a sentence, you tokenize it. So you can see, of course, some of these words are written as they are, but some are decomposed, right, further. And for each one of them, there is a embedding that is learned. And there are some implicit tokens also there, like a beginning of sentence, end of sentence, because you also need to understand where the sentence is beginning and where the sentence is ending, right? So some explicit tokens and some implicit tokens also there. So they recreate that. Why it is important to know, especially if you go to any generative AI model, right? Normally, if you see like OpenAI or Anthropic, they'll say, okay, tokens. Okay. So they charge $1 per 1 million tokens, right? They don't say words. Okay. So there's a reason why they're saying no words, right? Because they don't deal with words, they deal with tokens, right? So for example, if you you provide an input which contains 100 words, okay? So they don't charge for 100 words, right? They decompose that into tokens based on their vocabulary. So they would have built their vocabulary, and this vocabulary is not same across multiple different models. The vocabulary that OpenAI uses or Anthropic uses or Google uses could be very different based on how they are trained on. So they would have built their own vocabulary from the data on which they are trained on. So they will take your input and convert that into token, and based on that, they are going to charge money, right? So your 100 words could actually mean 200 tokens or 300 tokens or 150 tokens. All depends on how these vocabularies are built. So typically, one word is how many tokens? Depends on the language and the complexity of the language. Typically, English, one word is about 1.3 tokens. Okay. Again, these are approximate estimations. You don't have to, right? Like Hindi, of course, we look at Hindi if you know how to read Hindi little here. For example, this is 1, 2, 3, 4, 5, 6, 7 words, but you can see how many tokens it has created, right? This is much more complex language, right? So typically it generates about no, 6 to 7 tokens, right? And again, this conversion of words into tokens, they are not constant. As the trained model, as they understand the language much better, English probably remain mostly constant because English is almost everything they have used. But a new language samples, they collect more to train the model and improvise on it. They probably generate a new vocabulary. So they keep changing this particular sentences, right? OpenAI actually has a very nice link here. I'll just show you. For example, OpenAI tokenizer there. It actually tells you if you input a sentence here. For example, I'll just take this sentence itself, right, and put that. You see that? Of course, I don't know how many words are here. Let's take a smaller one. So 1, 2, 3, 4, 5, 6, 7, 8. You can see there are 8 words in this, isn't it? In the sentence, but it has converted into 11 tokens, which is approximately 1.3. And also shows you how the tokens. So open is one token, AI is one token, apostrophe S is one token, right? And the remaining also probably remains all same, and the full stop is also one token, right? And if you use some other language, it of course will show you much better. And you can see that different languages will have a different kinds of tokenization, different models, and different languages also, right? Let me see if I can. I don't know if I have. Yeah. So this is 31 tokens. In Hindi, what we better this 31 tokens. This is almost like 4 or 5 times of that, right? And this is necessary because, and the benefit of doing this is, one is with a smaller vocabulary, we can recreate almost every possible words in the world, even the new words that's coming up, because you have a sub words. And sometimes this also will take care of the spelling errors. So if you've observed in OpenAI, ChatGPT or any other generative AI models, even if you make a smaller mistakes in the spellings also, it takes care of that because it's not looking for the whole word. It decomposes that. So the decomposition kind of helps it to understand what the original word actually is. Okay, so that's a beauty of decomposing a word into tokens and recreating the words from the base tokens, right? It helps you to do two things. One is all possible words and can recreate almost all possible words. and it can also take care of spelling errors and all that. Okay, so the specific aspects I'm talking about, one is, of course, we understand what is an embedding is, right? It's a numerical representation of words. One is a parameter, because you will always be encountering these words when you use generative AI models, and one is tokens, right? So I think you have got some intuition behind all these particular concepts. Second one is there is something called polysemy and synonyms, right? For example, a particular word, right? A particular word like a bank, right, does not have one meaning, right? That means they um, do not have one semantic. The bank itself can change its meaning based on the context it is actually being used. So river bank, where the bank itself takes different meaning, or when you're talking about the money, it has a different meaning, right? So a particular word can also have a different meanings. The bank of a river or money in the bank. So what they do is they also generate something called contextualized embeddings. And these embeddings are generated from the base embeddings based on the neighboring words, okay, through a mechanism called attention mechanism, which is again a foundation of, you know, uh, generative AI models. Just to understand that how this attention is created without going to math and all that. For example, if you see here, the sentence, the animal did not cross the street because it was too tired. So when you look at it, who was tired? The street was tired or the animal was tired, right? So what it does is to understand the meaning of it actually looks at the neighboring words and which neighboring word has much more influence on the meaning of this. It actually creates an attention to that, larger attention. So there's an also weight here, which gets estimated in the process. So it's okay when you talk about it, the embedding of semantic of it should derive the meaning from the animal because it refers to the animal. Same thing here, if you see, the animal did not cross the street, same sentence, because it was too wide. The only difference is you just change one word here. Now the it has to refer to the street. It's not an animal, right? So this is actually incorporated into your transformer architecture, which is basically one of the mechanical attention. Okay, it actually learns how to give attention to specific neighboring words to derive the meaning of it, because the meaning of the word, a particular word might change based on what context it is actually used, right? So that's an important aspect also. So there are basically different ideas that has come over a period of time, which made generative AI, what it is today. I'll just explain this concept and then we'll take a smaller break if you want. Any questions? Adnan, do you see any questions?
Yes, we have one question from Yashwant, which is how do we assign context?
Yeah, this is actually learned, right? This is actually learned in the process. We don't assign manually. So initially it will be randomly initialized these weights. You can think like uniformly assigned. All the words will have an equal influence on this particular word, right? And then it will be learned which particular weight has more influence based on what the, let's say, the end sentence, right? Is able to predict the end sentence, then probably it will have more meaning, more context derived from the animals. So all these are basically learned in the process of the modeling.
And we have another question about modeling. Any reference to understand modeling concepts like attention mechanism, etc.?
Yeah. So that's a little more technical. If you want, I'll send you. I have videos of that. I'll send you. If you want, actually, one of the things that you must understand very deeply is some of these concepts are extremely complex. And if you want to dive technical, you have to learn how to code actually, right? So I'm not addressing that coding part here or mathematical concepts deep here because this is a manager's workshop. But if you want a little more deeper understand dive in, I will actually share those videos with you. You can go through that. Okay. So far we looked at the four different core foundational concepts, and I'm explaining these concepts which are essential for you to understand when you're building generative AI model. For example, embedding is one of the most important concept, right? Whenever you're building solutions, especially like RAG solution or whatever, your embeddings are extremely important concepts, right? How to convert the sentences, paragraphs, documents into numerical representations, right? So that's an important concept. In terms of tokens, right? This is also important, especially when you're looking at building generative AI solutions in terms of cost estimation, right? This is also important. And then parameters, okay? So how large the model is. This is again from the inference cost, right? Because larger models will have a much more inference cost. So the terms which are essential for you to understand when building or thinking about solutions, I'm addressing them at a very high level and intuitively. So not only the words are converted into embeddings, right? Even the sentences, paragraphs, right? The collection of words which creates a sentence or probably a paragraph or a document, right? They are also converted into embeddings. So the embeddings for the sentence, like the embeddings for a word, contains the semantic of the word. It actually, in a virtual world, right? In a latent factor word, it tells you what the word meaning is. Similarly, an embedding for a sentence, kind of tells what's the meaning of the sentence completely. Okay, which are more essential because you typically deal with more at a sentence level or a paragraph level or document level. Okay, even the documents, right? A document is nothing but a collection of sentences or paragraphs, one sample. So just to show an example of it, you know, um, uh, Hugging Face actually has converted the whole of Wikipedia into embeddings. So this is a nice project they have done, Hugging Face. If you look at any particular page, for example, there's a page called YouTube, right? There's a Wikipedia page for YouTube which explains what YouTube is. All right. And if you look at the YouTube page, they have decomposed into multiple paragraphs first. So this is the first paragraph in the Wikipedia about YouTube. And what they've done is they've converted that into an embedding space. You see that embeddings, numbers. Okay. It's on, I think, the dimension of, I don't know. They have not specified the dimension here. So they have actually specified all the numbers. So if you look at these numbers here, if you can see that numbers here, these numbers truly represent, right, collectively as a vector, the semantic of this particular paragraph, what the paragraph actually means, right, in that particular numbers. Okay. So then what you can do is you can do semantic similarity. I'll show an example, one classic use case here. Okay. For example, one of the direct, of course, there are many different use cases for embeddings. One of the direct use cases for embedding is basically search. So search is, of course, an important application, in the web, also in the different organizations. For example, product search. So whenever you look at a catalogs, right, e-commerce platforms and all that, right? So what typically people used to do prior to embedding is people used to do something called keyword-based search, right? Keyword-based search. Right? That means if you're searching for a particular product, let's say you say, running shoes, right? So they look at if any of the product descriptions or the product name does contain those particular word or not, right? If they contain, they will basically filter that and show those catalog or those results to the users. But sometimes what happens is the user may not exactly know which keywords or phrases are there in the product description, right? For example, if the people search for jogging shoes, right, and the product description is something like this, then probably it's going to miss this particular, you know, product, right? Because basically it's a running shoes. But running shoes and jogging shoes are primarily the same thing, right? So if you do a semantic based search, then what you do is you take the product description and convert into the embeddings, the numerical representation, like a vectors, right? And then whatever the user query is given, you also convert that into vector space, right? And you search in the database, this vector is very, very near. It's called a nearest neighborhood search. This vector is nearer to which other product vectors. So rather than looking at a keyword based or phrase based search, you simply do a vector to vector similarity. We normally use a cosine similarity for this. Okay. Again, don't worry about this. Okay. And a lot of these products nowadays, if you must have heard about vector stores or vector databases, right, which are coming now, which takes the text descriptions or paragraphs, they convert into numbers and store into databases. And if you query, they simply run a cosine similarity. They're much more different algorithms are there, like approximate nearest neighbor, ANN, even KNN algorithms, and say which actually has a similar meaning. Okay, so that way the search results are much better compared to the keyword based searches, because you're searching based on semantics, the meaning of what the query is, right? And sometimes, you know, you if you search for something like this, even spelling mistake also, misspellings, Bluetooth. Now, typically, this won't match in the keywords because there's a something is missing here, right? But typically, because we decompose that into smaller tokens, okay, it probably is going to match the correct product descriptions. So not only can take care of semantics, it can take some misspellings. In fact, it can also take care of cross-language searches also. Let's say user is searching in Hindi, and the word in Hindi is similar meaning as the product description in English. Also, of course, you have to train the models, and some models are actually embedding models are trained in multiple languages, so they tend to understand the similar meaning, especially language translation models, right? So they can actually find out the right product for it, right? So this is one of the beautiful application of embeddings where you can take care of if the keywords are different, if the spellings are wrong, the language is different, right? You can actually take all these aspects in the search. So today, if you look at all search algorithms, search products, whether it's called Google search, right, or even Elastic, right? If you know the products Elastic or Vespa, right? So they all have incorporated semantic similarity, semantic based search deep into their products, because that gives a better result compared to the traditional keyword based search, right? And sometimes people do both, which is quite popular now. It's called hybrid search, right? So it uses the traditional keyword, which is also called BM25 search, by the way, plus semantic, the embeddings based search. So they do both and find out the best possible results. And now the embeddings are not only limited to text, they also being generated for other modality. For example, images. So images are also getting converted into embeddings. The documents, of course, the audios, the videos, everything is converted into now vector representations, right? So the models which are called multimodal embeddings, which are used to create embeddings for different modality. Okay, multimodal means different types of inputs, the images, documents, or text, or audio, or video, everything. And then typically they use a vector representation to store it. And whenever you search, they search through that, right? um, if you're doing purely a search-based solution, embedding-based solution, for all these models, because nowadays people use a lot of these models actually, and there are a lot of open source models also there. There's typically something called a leaderboard, right? Let me show you. So leaderboards kind of do a benchmarking of these models and tell you which is a better model, right? Of course, they also tell you for what kind of tasks you can use. For example, Hugging Face runs something called MTEB. Okay, it's an embedding based model. It's called Massive Text Embedding Benchmark. You can see leaderboard. And this leaderboard basically tells you which are the better models. For example, currently, this is an NVIDIA model, Embed V2, which is the best accuracy, average accuracy across multiple tasks, classification, clustering. They also have given you, models which are specific to particular task. If you're doing only classification, for example, if you're taking a sentence and finding out if it is a negative or positive, you convert that sentence to embedding and feed that a model to predict, right? Um, or retrieval, which is probably the RAG. This is where the RAG will come. We'll look at that RAG little later. If you want to summarize, right? Different tasks are there. Some of the tasks we'll discuss later when you come to use cases and all that. So you can look at which are the models, and these models also has parameters, right? So this is, if you look at this, has 7,851 parameters. So it's a 7 billion or 8 billion parameter. Quite large for embedding. Embedding models, this is actually quite large. And this is the dimension. What's a dimension? The dimension means, if you come back to our prior example that I given you earlier, let me, yeah, if you look at this example, he's embedding for the word CEO. So this is the dimension 1, 2, 3, 4, 5, 6, 7. So this is 7-dimension representation for the word CEO, right? And for the word men and women, the example that we did is 1, 2, 3, 4, 5, 6, 7. Again, 7-dimension here. Okay. This is only for demonstration purpose. The real world, they are quite large. So you can see this is about 4,096 dimension. So a sentence, if you give a sentence, it gives you that many numbers. So that's a representation of that embeddings. Quite large. There's some 8,000 also there. All right. And max token, that means how large text you can give to embed. Okay, you can't give more than that. Plus 32,768 words. Tokens actually. Again, see, everything is tokens, not words. Okay, that's why I'm explaining these concepts of tokens, parameters, because wherever you go, embeddings, you will always find these concepts that you might have to, take into account when you're building solutions. You have to take all this, understand these concepts clearly. Okay, so let me see. We'll finish this embeddings part and then, yeah. So there are two kind of models you will find. Okay, most of the times when we say generative AI, you mostly think about GPT, right? That's one kind of model, right? But not necessarily. There are typically two kind of model. One is called text generation model, which is your GPT-4 or Chat GPT, or your Claude model from Anthropic, or your Gemini model from Google and all that. But there's also something called embedding model or text representation model, right? The two different kinds of models everybody offers. And if you look at OpenAI also, let me show you OpenAI models. You search for OpenAI models, you can see there's a set of models here, GPT-4, 4 Mini and all that. So these are, of course, your text generation model. What is a text generation model? A text generation model is given a text, right? Given a text, which can be, a sentence, or can be a question, or can be a paragraph, whatever, it completes it. right? For example, you ask a question and answer the question, right? So given a text, it generates more text. These are called text generation models. Okay. Typically, your generative AI model is identified with this. Most people, when you say generative AI, they mostly refer to text generation models, right? You ask a question, it generates a text. That's the foundation of it. But sometimes when you give a text, it only creates a numbers. Okay. And these are called embedding models. In fact, if you look at OpenAI, they have a set of embedding models out there, right? So if you give a text, it just generates a number. So this actually helps you to build solutions like RAG and search and other kind of similarity, where similarity is important, semantic similarity in the builder model. We'll talk about other models also, like for image, text to speech, moderation, and all that later. But if you look at the paradigm, there are two kind of model. One is to generate text, one is to represent text, right? And they're also called, by the way, when you have a discussion with customer or probably discussion with technical team, they also use something called encoder model and decoder model. So encoder models are typically your embedding models or text representation models. So given a text, they know how to represent that in terms of numbers. Given a text, they represent, they generate more text to complete that sentence or answer the question. They are called decoder model. So these are again text generation model. Okay. So these are different terminology people use. One is people text generation, text embedding, encoder, and decoder models, right? And majority of them are basically your decoder models. Okay, I think we will take a small break here and we'll come back and look at the remaining part of it. Okay, can we take a 10-12 minutes break here? 9:55 will join.
Okay.
The next question.
Next question is, what kind of data are these generative AI models trained on?
Okay. It's also important that we to answer the question, because over a period of time we have seen these models generate these embeddings, the representations, and they also generate text. I think we are already familiar with, and most of us would be using ChatGPT, and how coherently and how beautifully they generate text. And what is the uh, how they're actually able to do it, right? One of the questions that you might have, which is also essential for to understand when we build downstream applications, we might have to mimic some of the steps that they have done to kind of customize these models. Not necessarily GPT-4, but there are many models are of similar or probably little lesser capability, but appropriate for our downstream business applications. We might have to recreate or mimic some of the steps, right? And we'll also talk about that, when to do that and when not to do that. So it's essential that we understand how these people have actually built such a wonderful models, right? What are the overall high level steps involved in building these models, like ChatGPT or Gemini or Claude, right? Very high level for our understanding. So uh, actually, it comes from two important understanding. Is this particular text, right? This particular graph tells you uh, how data is very important for building these models, right? If you look at the amount of data and the model's performance, okay, so these models are actually measured based on certain metrics, which will explore in the subsequent sessions. So, is there a relationship between the amount of data and the model performance, right? If you look at the traditional ML algorithms, which are traditional, basically nowadays, traditional means non-deep learning models. They're called traditional. Your decision tree models, your random forest models, your boosting models, regression, all this linear regression, all the models are typically called traditional ML. And they also have a relationship with the amount of data. Of course, if you use too less data, the model's performance will be below par. And as the amount of data increases, right, typically these models tend to have a better performance. But there will be a point where they saturate, right? That means they don't learn much. The, the marginal increment in performance, right, uh, it's not significant compared to the amount of data that we keep ingesting to these models, right? So traditional ML models are they saturate over a period of time. So of course, this is an optimal amount of data that you should give to the traditional models. But what is this optimal size? This depends on the model, depends on business use case, the complexity of the problem. There is no thumb rule like this. Okay. But typically the number of samples that we use, number of samples, okay, again, thumb rule, it depends on the complexity, is a function of a number of features, right? But if you look at your deep learning algorithms, there is something called n small deep learning neural network models and a large. Your LLMs are actually typically fall under this particular domain, large language models, large models, right? This is typically anything lesser than 1 billion parameter. This is more than 1 billion parameter. Again, thumb rule. So they tend to learn better. And large language models, they keep on learning as you feed more and more data. Okay. That's actually we call scaling loss, right? In fact, if you have read news lately that we are actually hitting a wall of data, we don't have enough data to train these models. We have almost used all possible data that's available. So now people are creating synthetic data to train the models. We'll talk about little more synthetic data in the third session and all that. But just to give a precursor to that. So as you know that the amount of data is a very important factor for improving the model's performance. So what they do, they use a lot of data. So if you look at a llama model, okay, first of all, there is no published information on proprietary models like a GPT, Gemini, and Claude. So they haven't published how much of data they have used to train these models on. Just to confirm, are there any background noise or is the audio is clear?
It's clear, Manranjan.
It's clear.
Okay.
It's clear.
Okay. So there is no published information on proprietary models like GPT, Gemini, and Claude. But we assume that there are much more compared to the open source models. So Llama is a series of models released by Meta, which are called open weight models. They are not open source. Again, I'll come to the difference between open source and open weight models. What are they? So they release the weights to the public. So these guys don't release. They only release an interface through which you can ask questions, right? So they also have different kinds of model, like 8 billion parameter model, 70 billion and 405 billion, is the largest open weight model so far. Okay. And the amount of data they're actually trained on is, if you see, 15 trillion tokens. So that's huge. So if you look at the amount of text data they have used to train these models, if you take the words or the tokens, in fact, again, tokens, okay, you count them, that will be 15 trillion plus. Okay, that's the amount of data they have used to train these models. It takes about 2 to 3 months just to train the model, right? And huge amount of compute is necessary. But because they're trained on such a huge amount of data, so they understand these languages, the complexity, the language understanding, the representation and generation so well, actually. And there is actually a nice paper published by Google DeepMind Okay, DeepMind is one of the important companies which is acquired by Google. They do very advanced research. In fact, before OpenAI, they were the leaders. Well, now they are leaders actually. In fact, if you have heard the news, there are two deep learning model researchers, in fact, the co-founders, one of the co-founder, they actually awarded Nobel Prize in chemistry, right, for using deep learning models to predict the protein structure, right? So they actually come from Google DeepMind. So they have published a paper called Scaling Laws for Neural Language Model, right? That means if you look at the three different factors are important. One is how much compute, how large machines you use to train the model. What's the data size? How many tokens you input as a data? And how large are these models, parameters? So these are three important, factors. So whenever you look at how large the model is, 1 billion parameter, 2 billion parameter, 10 billion or 100 billion parameter, how much data we have used to train these models, and how long and what the infrastructure that we used to train these models. And if you look at all the three graphs, they have actually, as the compute increases, right, and the parameter increases, what is the loss? Okay, loss is inverse to the performance of the model. The lesser the loss, the better. You can see as you increase compute, the loss decreases. Data size increases, the loss decreases. The parameter increases, the loss decreases, right? So they have shown empirically, this is not theoretical, it's empirical evidence that as you increase more compute, more parameters, and more data, typically the models tend to learn much, much better. But then what kind of data? Is it all same data? Okay. So there are multiple different data sets out there. So there are two data sets I'll talk about, the open source data sets. One is called the pile. Okay, this is one of the open source data which is available even for us to download and train our models, right? And these models are trained on, if you see the kind of text they have used, right? All possible text which are representational, sorry. What's this? Which are representational, right? For example, they have used data from PubMed journals, which are healthcare, medical science journals. All possible books, I think there are about 15 million books or something like that. Archive, I don't know whether you know this site called Archive, which is actually a repository of all science journals, right? Published articles. GitHub, which is the code. Free law, which is also legal, the legal perspective, all the articles and journals. Stack Exchange, where people ask questions. This is almost like your Reddit or Stack Overflow, right? Wikipedia, the whole of Wikipedia they have used. Book Corpus, they have used two, I think, Books 3 and Book Corpus, these two. YouTube subtitles, Hacker News, right? You can see even some of those other data sets like NIH, right? You can see the amount of representation. So they have taken different kinds of data and trained these models on, right? This is, of course, an older data, which is, of course, you can build models on top of this. But the newer data is there's something called fine web data set, okay, which is recently released by Hugging Face. And this contains about 15 trillion tokens, okay? And they actually, the basis is Common Crawl. So Common Crawl data set is actually a project which crawls the whole internet, right? And it crawls and creates a repository of snapshot of the whole internet from 2013 to 2024. It's about 10 years of internet data, web pages, news, articles, blogs, educational content, amounts to almost what? 15 trillion tokens. This also gives some indication into what is the amount of effort people have put in as a community to kind of, which enables these models to work so well. So we only look at the end product, ChatGPT, but before that, the last 10 years, the amount of effort that has gone into curating this data, preparing this data, studying this empirical evidences that more the data is, the better the model is. And of course, some other things like infrastructure, like a GPU and all that, right? So this is the data, of course, is available, is freely available. And this is again available in the Hugging Face. I'll show you. And you can see the data size is about 44 terabytes of disk space, right? Significant amount of data. This is cleaned, deduplicated, right? Normalized data, removed all the unnecessary characters, right? Deduplicated, everything is done. Simply input the data to train a model. But this needs a significant amount of storage and compute, which is beyond the reach of most of the organizations. Forget about individuals. I'll come to that cost of implementing the solutions also. Yeah. So just because we have trained on such a huge amount of data, these models have learned so well. Okay. Next question. If there's any other question.
There is one question we had from Atul, which was why should an increase in compute only decrease loss? Won't it make it faster only? So why should compute decrease loss on those graphs with Google's loss graphs?
Yeah, that's an interesting question. So what happens is when you typically you increase compute to do one thing. So if you look at the models, right? I would look at the models. When you input the data, text data, right? And this is your model, right? Let's say this is your 10 billion parameter model, right? And this is, let's say you're doing a next word prediction. Or ultimately, you have to build a model for an objective, a purpose. And this is the loss. That means if it's able to predict the next word or not, right? Most of the times what happens is because of the limitation in infrastructure, for example, of course, you can't build it for infinite period of time, right? This loss, typically you come to only a certain point, right? You can't train the model more. But if you increase the infrastructure, what happens is you do more iterations. So typically the way these models learn is an iterative fashion. So you give the input data, you calculate loss. The loss is very high. You do a back propagation, which adjusts the weights. Again, input the data, again calculate the loss and do. So it's multiple iterations, right? So if you increase the compute, typically you are able to do more iterations, right? The number of iterations are typically done more. Probably running, let's say, 10,000 iterations, probably are doing 1 million iterations, right? So that's why you can see the losses. The more iterations you do, you can see the losses going down. Okay. So here, in terms of more compute, means basically you're doing more iterations. Okay. What's the next question?
The next question is, generative AI models are trained on such large text just to predict the next word, or is there more to it?
Yeah, that's an important question. So far we have understood that we take a model and take all this data, right? And you kind of create this previous word and predict the next word, previous word and predict the next word, right? But then, uh, you know, uh, if you take a particular example, let me first explain that the different steps here. So typically there are 3 steps involved in training these models. Okay, we'll talk about 2 stages today. The third stage we'll address in the last session or third session, a little more complex. So there are 3 stages involved. One is called pre-training stages. Okay. So pre-training stages is mostly the predict the next word. The given the set of words, you predict what is the next word. But following that, which typically trillions of tokens, right? Use that. But once you train the model which can predict the next word correctly, then it goes to something called instruction fine-tuning. Okay. So here, the model is actually tuned to prompt and response. Asking a question, right? It gives a response, right? If you have to understand what exactly are this is almost like analogous to imagine in school or colleges, we read a chapter, right? Isn't it? We read a chapter. When reading a chapter, we make sense of the ideas and concepts and everything. So you understand what is the core ideas and concepts explained. But based on those ideas, if you have to ask a question and to respond, if you see every end of the chapter, there is an exercise. It's given a question, how to answer the question based on the context or information given in the chapter, isn't it? The kind of practice questions. So you can think like instruction fine tuning. The next stage, where once the model has understood the context, the words, semantics, everything, how to respond to a question based on that, right? So pre-training is, for example, here, let's take a small paragraph here. This tells you a stock represents ownership in a company and is traded on a stock exchange. The price of a stock is influenced by many factors like company performance, market trends, economic conditions, and all that. Bonds, on the other hand, and debt instruments are investors that lend money to exchange of specific interest payments, and so on. Diversification is a key strategy to reduce risk in an investment portfolio, right? So here, if you train the model on this, it'll learn how to predict the next word. So only if you can give this sequence of words, it'll say, okay, the next word is and. But a lot of concepts are there in the text, right? For example, it talks about which factors are influencing the stock, isn't it? What is mostly a bond, right? What is a diversification strategy, right? So if you ask a question something like this, what is the primary purpose of diversification investing? Okay, the model will not be able to respond to that because it has the knowledge, but it cannot generate that text because all it has learned is what? How to generate the next word, right? So what you do is now, once the model is trained on this, it understands the context and all that. Then you train on a set of questions, which are called prompt and response pairs, right? And this prompt and response pairs, like you manually or synthetically through any means, you generate certain questions. Like what is the primary purpose of diversification investing? To reduce the risk of an invest portfolio, right? So this is basically called your instruction set or prompt response pair. Again, you fine tune that pre-trained model on top of that. This is almost like reading a chapter. Then kind of building an expertise or and enhancing your skill by doing a practice exam, right? Very similar to that concept. So, for example, can you analyze the sentiment? The company's quarterly earnings surpass expectation, driving price stock. It's a positive sentiment, right? Can you model summarize? Because when you actually use these models, we can do quite a few things. We can ask him to answer a question. We can ask him to summarize that report. We can ask him to classify it's a positive or negative. So you fine tune that model on multiple different tasks. Okay. So that's what basically you do. The model is first pre-trained on a large corpus, primarily to predict the next word. What is the next word? And because we are running on trillions of tokens, right? So these models are typically get a good understanding of the text, but they're still not, capable enough to answer specific questions. And the way we answer questions are very, there's a pattern to it. Question, answer, summarize, extract information, classify, right? So then what you do is you train these models on top of that. But you typically don't train it on a very large corpus. There is an understanding that about few thousand or 100,000 prompt response pairs is good enough to get that model understand how to respond to questions. Okay. So pre-training is like a reading a chapter, acquire a broad and general knowledge by looking at the corpus, okay, which develops a comprehensive understanding. But fine tuning is like doing exercises, applying and refining knowledge, focus on target and task specific data, how to respond to it, right? Do that. So now how to do that? Again, there are, this is the step actually which differentiates companies from companies. So OpenAI has invested a huge amount of money, and they've hired probably thousands of data labelers or experts and all that, right, in different domains. For example, there'll be people for legal domain, finance domain, math, creative writing, right? So many different areas. So they will ask them, generate a lot of questions and ask them to write them, okay, in a manner that will be appropriate for humans to consume or probably downstream systems to consume, right? So they have invested a huge amount of money, but they won't open source the data. They have not open source the data, by the way. And none of these proprietary models, they have open sourced the prompt response pairs, right? But there are also open source data there, which the models can be trained on. For example, there is a Databricks company, which is a dataset called Dolly dataset. And if you look at the dataset here itself, right? And, you can see there's a question, there's a context and a response. So given the question, along with some additional information, what the response should be, right? So, and if you look at the category of types of questions, there are some classification. For example, which is the species of fish? Tope or rope? I don't actually know the concept here, but still, it's a classification problem. There are some open-ended questions you can ask, like, why can camels survive for long without water? Okay, there's a response to it. So this concept, the model would have already learned from the corpus, like a Wikipedia, but doesn't know how to answer this question in a specific manner, right? Which we learn here. But then we don't need to learn for every possible concept. If you can tell the model a specific examples and train them, so they will able to understand and do the same response pattern or style for all the knowledge that it is learned from the original corpus. So there's a closed QA. Closed QA and open QA is closed QA means you answer the question from the text given. Open QA means just ask the question, let it answer. Information extraction, given the question, just extract some information. Brainstorming, right? You can see there are summarization, right? So they actually train on multiple different tasks. So this is one of the questions that Atma asked earlier, saying that how models are able to do multiple different tasks, right? Because they're trained or fine-tuned on different possible tasks, okay, in the process of fine-tuning itself. There are many different data sets are there. Some are open source. For example, this is a Databricks which gives you 15,000. They are called prompt response pairs. If you look at a chart GPT, you give a question, it responds with a response, right? So similar pattern they would have been trained on. Alpaca, which is about 52,000 prompts, which comes from Stanford. Google has released, but of course they're using beyond this also. They have internal data for Gemini model, but they've also released certain data sets. Like a FLAN, 1.8 million examples. This open Orca data sets about 3.3 examples. Recently, as a Microsoft also released about some millions of instruction data sets in open source. Okay. Any questions?
Abhilasha has asked, the list you showed for Databricks Dolly, all is already there in Dolly.
All is already there means, can you elaborate on that question?
Just to confirm that everything they have already done and implemented, like we just go ahead and use it.
Correct. And if you are building a model on your own and you want the capability of the model around these specific categories of tasks, let's say. Then you can actually take this data set and train your model on, or probably can little bit improvise. So you can generate some more, like 1,000 or 2,000 more data set, which are especially for you. Then you can train on, right? The data sets. You can always add on to this and do it, but not exactly you will take, and train the model on the same data set. You have to understand that what is the model's objective. We look at one of the flow chart now, when to use a model and when to fine tune it also. Mhm. Yes, yes. Yeah. What's the question?
We have one that says, suppose we want to fine tune a model for healthcare. Is there a resource where we can get open source healthcare prompt and response?
Absolutely, you can get. In fact, if you go to Hugging Face, right? Hugging Face is basically the repository for open data sets and models. If you see, we go to Hugging Face here. On top, we can see a model and data sets here. And you can click on the data set and you can actually search for it, right? So if you say instruct, you can see that so many instant data sets are there, right? So there are about 4,583 data sets are there, instruction data set. But you can also look at like a medical, right? Data sets. So there is already data set for medical chatbot, right? Healthcare, right? So how to chat with the doctor, it is all data sets already there. Healthcare analysis and all that. There will be also for finance. No, I think wrong spelling is wrong. Yeah, you can see finance instruction data is about 200,000 data. The clean data also there. But you see, some of these data sets comes from an individual. So you can actually use the data set as a baseline and do some analysis. You still have to do some kind of cleaning or add to the data set your own specific set of questions, but you may not have to start from scratch, right? So a lot of data sets are already available in the Hugging Face, which you can take as a baseline, do some analysis. Does it kind of solve my objective of why I'm building this model? Okay, is there kind of a prompt response pairs or instruct right sets are there which kind of aligns with my objective of why I'm building the model. My model should answer which kind of questions. Okay, you'll probably get quite a few of that in the existing open source data, and then some probably you won't get, so you still have to add that. Okay, that's an expensive step, of course, if you would add, because you have to hire annotators, domain experts to do that. But you may not have to do it from the scratch. Okay. Yeah. Answer the question. Any questions?
I think there's no further questions. The next general question we have is, do we ever need to build our own foundation model?
That's an interesting question, right? But before that, I'll answer one more question to kind of get a sense of what it takes to build a model. So even if you even go that path or not, so how much it costs to build a foundation model, right? So a typical bill of material for building an LLM, okay, is you need data, compute, and people. Of course, these three different aspects, right? So you have to, all these three aspects are going to cost you money, right? So data in terms of licensing and purchasing, let's say legal or finance, right? Then you have to go and procure this data. So there'll be a cost for licensing and purchasing. I'm not specifying how much it will cost. That I'll give you some approximate estimation, but you should take it a pinch of salt. But I'll tell you the bill of material. Then data preparation. This is a huge effort. This is it can be cleaning the data, even annotating the data, right? Which will actually cost you a lot of money. Then compute. Most people, you cannot train your model in-house. because it needs specialized hardware like GPUs, which are very expensive and probably not available to build on your own data centers for most of the organizations. So you typically go to cloud. So you need a cloud infrastructure. Storage is required for your data storage and model storage, which are not very expensive, but GPUs are extremely expensive, by the way. I'll come to some estimation. Then in terms of people, you need, there are four kind of people you need. One is data annotators, especially for people who have to annotate the data. These are typically domain experts or domain people, right? And of course, you have to define certain guidelines. We'll again come to that when we talk about some example. Then, of course, you need AI engineers. They are extremely expensive. These are most expensive people in the world today, right? I mean, these are not AI engineers who write prompts. They are AI engineers who actually know how to, train a model, right? So they are AI engineers. DevOps, because you are using a cloud infrastructure, you have to need a DevOps people who provision, maintain, do support of the infrastructure. Then you also need a people model evaluators. These are, if you ask me, what is the most important skill that's going to be in 2025? Okay, for me, model evaluators, because these generative AI models are, there is no specific way to evaluate models. They're extremely fuzzy, and we'll actually spend some time how these models are evaluated in the next session. So model evaluation is becoming one of the most important skill in the in the coming years. Okay, so these are again people who understand domain very well. Okay, so the set of people, you need data annotators and model. In fact, they can be the same set of people who can do both the tasks. Okay, and expensive components is GPU cluster, AI engineers, and instruction data set that we create for fine tuning, which comes from these two different components. I mean, if you ask typically how much it takes to build a 1 billion parameter model, just to in comparison, GPT-4, we don't know, but there is a estimation that it could be 1 trillion parameter model. That's 1,000 billion parameter model. Okay, your llamas are 400 billion parameter models. The Gemini and Claudes are almost like 500 billion parameter models, right? So that's a large. So to build even 1 billion parameter model, right? Typically, the estimation is data acquisition can come up to so much, especially based on if you're doing a domain specific. Okay, there's no reason why you would do otherwise if it's not a specific domain, right? And cleaning and all that might take about 3 to few months, and then probably need some data. The most expensive components are your AI engineers, which charges a lot of money. Okay, and this is of course US actually. India could little differ. Then GPUs. So GPUs are typically about 1.5 to $3 per hour in cloud pricing, and you typically need about 30 to 64 GPUs for training 1 billion parameter model, and typical time is about a month to train these models. And these are the latest GPUs which are available from NVIDIA, which can be used. Again, this cost would vary. You can see the significant lower bound and upper bound. And this is again a rough estimation. Don't take it very seriously. These things keep changing. The cost changes, the cloud changes, but roughly this is, but you can read these two articles a little more, which goes in details about estimation, but this keeps changing, but this is about a rough estimate. So about $2 million you need if you want to do from pre-training. Okay, this is not fine tuning, from pre-training to the final foundation model. So if I want to build a foundation model. Now coming back to the question of what Atma asked, do we need to build a foundation model? Typically, this is a flow chart we follow, okay, that I suggest. Most of the times you don't build a foundation model, okay? This is the last step that you do. And you take other things. For example, the first question that you need to ask is, do you have a domain specific requirements that general purpose models cannot meet? All right. Now, how do I know which model is built on top of that? We'll come to that again. So let's say you want to build a model. So you want to create a solution for which you need a model, and most of the models are not trained on that kind of data, right? For example, there's a model that Bloomberg has built only for finance data, right? So your general purpose models cannot meet. Okay. Yes, then of course, otherwise, no, you don't need, then you simply do a prompt engineering and solve your problem, right? If it fulfills, you can take a general purpose model, you go to prompt engineering, you experiment with different prompts. Okay, there's a process to also the prompt engineering. You do that. But when you do a prompt engineering, you always choose an evaluation metrics and evaluation data set also, right? Most people don't do it actually. This is one of the biggest challenge. We call it a vibe check. Most people, when they write solutions using prompt, they do a vibe check. They check couple of data and they say, oh, it works fine. It doesn't work in the real world like that. You have to create a very, rigorous evaluation set which represents all possible scenarios, and you have to run your, prompt engineering. We'll come to the evaluation best practices later and metrics. And then you run that evaluation set on the prompt engineering. And if the model performs poorly after prompt optimization, all possible prompt optimization you have done, and still performs poorly, then you can take the step of fine-tuning a model, right? Then you say, okay, because the model most likely doesn't perform well is because the model is not trained on that particular task, right? Then you fine-tune it, okay? It's a fine-tuning model, and then of course it works well, it's fine. Fine-tuning is much lesser expensive, and it does not need millions of data points. Probably few thousands is good enough. Again, I have a specific example of fine-tuning an OpenAI model. I'll show that. If the fine-tuning also doesn't work, the prompt engineering doesn't work, you go to fine-tuning. Fine-tuning also doesn't work, then you think about building a foundation model. Or at the beginning itself, if you know that it's a very domain specific, which none of the general purpose models can fulfill, then you go to the foundation model. All right. But before building a foundation model, you have to ask this question: do you have sufficient data, compute, resources, and funding? Because this needs money. Most organizations cannot even fulfill this. Okay. If you have everything, then you go and build a foundation model. Otherwise, you can take something called hybrid approach. It's called data augmentation and domain adaptation pre-training. Okay. So you can take a pre-trained model and pre-train it again with your domain adaptation, right? Like you see, there is a model which is already pre-trained. You can take the stage 2 of pre-training, right? You can do one more pre-training, only your domain data, right? And then you can come to instruction fine-tuning. That's also possible there, which costs little lesser because you don't have to pre-train from the scratch. But this is also going to cost little more money than simple instruction fine-tuning, but not much. And I will show you all models do not provide the pre-training models. Some open source models, when they train, right, the model they get out of pre-training stage 1, that is also they actually release it to the world. Like Llama, they probably have there's also the model comes out of fine-tuning model, they also release. So they release the model versions at the end of every stage. Okay. You can only take those models and train it. Like OpenAI, you only get the final model, right? You can fine-tune it. You don't get access to the pre-trained model, right? Typically, open source model, you will get access to the models at a different stages. In the next session, what we'll do is we'll actually go through one proprietary model like OpenAI and Anthropic and one open source model and look at the complete landscape of what are they providing. So they'll get a much more clear picture of that. Okay, so this is typically you follow to build a foundation model. Some people have actually built domain-specific models actually, right? For example, Bloomberg has a built for finance model, right? But it's not open source, so you won't probably get access. Google has built a model for healthcare called MedPAM, which is quite popular. There's a company which works with OpenAI and Harvey. PwC has built their models. But there are also open source models available. You can search on the Hugging Face. Okay. Now, I think somebody asked a question, which model is a better model, right? It's a very hard question to answer unless there's no clear leader, right? It's all task specific. But at least to get a feel of which models are currently doing better, there are leaderboards which are there. Like you have a leaderboard for embedding model, right? Remember, I saw you in the embeddings when we discuss embedding called massive text embedding model, MTEB. There is a leaderboard which run by Stanford or Berkeley, I don't remember actually. So this is called LM Arena Mod Benchmark or leaderboard. This is a continuous process of evaluation. This is a community-driven evaluation for best LLM and chatbots. All right. And if you see, the last cycle of evaluation was done on a 2024, just 10 days back, 21st of November. And the way they actually evaluate the model is you can also go ask questions, right? So this is called Battlefield. You can ask your prompt, you can ask a question. What they do is they randomly choose two models. Okay, they won't show you, otherwise you might be biased. So let's say they chose a GPT model and Gemini model here. I'm just giving, right? So generate two different responses. And then you go and say which one you liked. You can select that one, right? Without any bias. Screen is not shared, same. Are you guys not able to see the screen?
I can see the screen.
Okay. Atul, can you check if the connection is okay? Yeah. So this way they actually, completely evaluate the model on new questions that you are asking, by the way. And you can't also select a specific model and create a bias because you don't know which model response are getting generated. You just say model A and B, but internally they will know. Based on that, they actually they use a score to find out which models are good. And they have already used like a 2 to 3 million votes, right? And they test about 169 models. This is much more reliable information. And then you can see, as of now, the Gemini model is the number one, along with ChatGPT. Both are almost number one. This is a score, but this is a confidence interval, like a plus or minus. So if you look at a plus or minus, these two scores are pretty same actually. They are not extremely different. They're part of the same distribution only. And that's why the ranking is upper bound ranking is these two are one. Then Gemini, then O1, you can see the models, all right? But this is an overall task. They also give you also category wise. For example, you can also look at for a specific task or specific language, which models are good. Like a math, instruction following, coding, creative writing, okay? These are not domain specific because they are doing a general purpose models. For example, the overall models, these are the players, all right? You can see the key players now, especially most of them, you can see most of them proprietary models, except probably Llama, which is again, fine-tuned by NVIDIA. This is not meta model, but this is open source model. Okay. Open weight model, by the way, not open source model. But most of the proprietary models are doing much better compared to the other ones. But if you see the difference in scores are also not very different. The open source models are also quite catching up, right? Recently, there is a model from Alibaba which is doing pretty good in coding, but I think they have not evaluated so far. This one, but I think it's an older model. So you can actually find out which models are doing good. And if you are looking for only open source models, then there is a leaderboard run by Hugging Face. Hugging Face LLM leaderboard, right? Open LLM leaderboard, which only compares the open source models. You can check, that which open source model is better. There are also some leaderboards are coming for domains, especially for finance and legal, but I'll show them later. So for example, if you look at this particular model, is doing pretty well now, in open source models, right? And you can also choose which specific task to deploy. And we'll look at also how they're evaluated little later. What are different tasks on which they're actually evaluated. This is average across general purpose tasks like this. Like some are the math tasks, some are question answering tasks, right? Language understanding task, and so on and so forth. Okay. What is the, is there any question?
There's one question which is, can all open source models be downloaded and run locally on-prem?
Yes. Open weight models. You can always download those models and run locally. There is a inference engine called Olama. We'll do that on third day. I'll show that how to do it. Now, if you take any particular, let's say this is the model that you want, you can click on that. You go to files and you can download these models. Okay. The models are quite heavy actually. They need significant amount of resources, but definitely on-prem you can do it. You can see you can download them. There's also an API based to do that. You can do that. Okay. So open source models are open weight. So different, okay, I think somebody's asking difference between open source and open weight, right? Open weight
Yes.
models are the models whose only the weights are available to download it. But how they're trained, what data set, the code to train them, how the actual steps to train them, right? If they are not available, like a Llama, they don't give anything except the model which you can download and run it. But which data set they're trained on, which data set they're fine-tuned on, what is the code, even the code to train, so that you can reproduce everything on-prem, right? Then they're called open source models. So open source models are basically when you have everything, all resources are given to reproduce on your own in on-prem or whatever yourself, they're called open source. But some models, they're trained, but the data set, the code is not given, only the model is given to be downloaded, right? They are called open weight models. And then there is proprietary models, nothing is given, only an API is given. You just send your question, they'll send the response back like a GPT, right? So they are called proprietary models, right? So three different kinds of models: open source. So one is open source, one is open weight, right? And then of course the proprietary models.
Pradhan, can you just please repeat open weights? Slightly not clear about it.
Open weight is the model that you can download and run it on-prem. Okay. So ultimately model is nothing but the parameters, right? In neural networks. So you can download and run it on your own locally, are called open weight models. But they have not given on which data set they're trained on. They might have told, okay, there's a data set, but the data set is not given to you. The code that the model, right? Code how they have trained the data, trained the model, that is also not given. Then it's called only open weight model. Sometimes people give the model weights and also the data and the code, right? The implementation of that, so that you can also reproduce the whole building of the model in-house, which is of course not essential for everybody. They are technically called open source models. Okay.
So which model can provide us the code and the data both? If is there any model they are totally open, like on
Yeah,
their
yeah, yeah.
code?
Yeah, there are some models out there. I'll show you an example of that. Okay, so there are some models you can simply build from the scratch. Of course, you need to have infrastructure to do that, but you can do it on your own. Completely reproduce from zero. You can reproduce that. Okay, I think Q1 models are, I think, one kind of model where you can reproduce everything. There are not many of these models, open source models now, but people are now pushing for it more and more. So you'll find a lot of proprietary models which are business oriented and people don't, want to train or anything, simply send prompts and get a response back, like your Anthropic or OpenAI or Gemini models. There's some models like Llama which can download and infer yourself. Okay, you can also fine tune them, by the way, but you can't recreate from the base. But some models you can do everything.
So you just mentioned about Llama. So Llama can be downloaded and fine tuned, but do they share anything more on their data set on which they have trained, or that I have
Oh,
to provide to it while doing the fine tuning?
fine tuning, anybody you have to give your own data.
Yes.
Yeah.
Yeah.
So that's why they're called open weight models.
Okay, that's also. And for verification, any like I have created, I have fine tuned everything I have done, but for the verification that whether model is working fine, uh, how can I? What should be my approach for the data set? Because getting that data set is also a challenge.
Yeah, we'll talk about model evaluation. So later, so model evaluation is an important step in adopting models. Even when you are not building or fine tuning yourself, even for prompt engineering, also model evaluation is important, right? Because if the prompt is giving the appropriate response, right? And especially like the example that we saw in the restaurant feedback, right? So you have to curate like 100 or 500 feedbacks, and then manually you'll see, okay, this is about food quality, this is about hygiene, this is about customer support, positive, negative. That data set you still have to curate, still at least for evaluation, not like for training, at least 500 test samples. And then when you send a prompt and asking him to classify, the model to classify, then you compare with your evaluation set, saying that, okay, if my prompt is appropriate, is it able to cover all possible aspects, right? You still have to curate manually, or you can also synthetically do it. Okay, there are also other mechanisms also there, right, to evaluate models. It's called LLM as a judge pattern, but we'll discuss that a little later. Okay, evaluation part. Okay. Any other questions?
There's one final question you've given, which I believe is quite similar to what was already asked, which is any examples of custom foundation models which are domain specific?
Yeah. Which are, we just saw that. No?
Yes.
Yeah. But you can also see quite a few models in the Hugging Face. For example, if I go to models and say legal or law, you can see that quite a few models are there. Okay, and you can check which model. Of course, a lot of the models are by individuals, which of course you can't use it. But some of the models you can you check by organizations, right? And when you go to the model, no, you can also look something called model card. Okay, so this is the like a contract of the model. Okay, so here they'll talk about the model and also what data they have used to train that, so you can get a feel of what the model is actually trained on. Does it align with your objective or not? And sometimes they also give the licensing terms, right? Whether you can use the model or not use the model for commercial purpose, right? That also you have to look into. If not specified, I think mostly you can use it, but you still have to check. Are you they're saying that okay, if you want to cite this model, you can use it, but you can cite the model. All right. And some disclaimers also there. So anything uh, risk arising out of the model uses, they are not liable at all. Okay, which is of course true for most of the models. So you can go to a model like a finance, all right. Somebody has fine-tuned the finance model Llama 3. You can check the model card, right? And examples. But most importantly, actually, you have to look at the licensing and the data that is trained on and what is it actually capable of, right? All those things you have to look into in the models. Okay. Besides that, of course, there are foundation models are there, commercial ones, which of course you can use, like a Bloomberg GPT, Harvey, or MedPalm, right? These are different models. I'm not sure MedPalm is an open source model. It's not. Okay. So, any other questions? So today's session was kind of, setting the foundation, understanding some of the key ideas and concepts, how these models are built. And now building on this, right, we will start discussing now, two things. One is in the next session, if I take a proprietary model, what are things you can do? So we'll actually go deeply into what are different offerings of the model of that provider. Like you will go to OpenAI and we'll also look at Llama or maybe Claude, time permits. Then we'll look at some of the high level prompt engineering, what we can achieve through prompt engineering, some of the prompt engineering best practices or patterns. In fact, there's a lot of guidelines given by this model providers also. And the prompt engineering styles also differ from model to model, certain aspects. We'll look at that. And then we'll start looking at solutions or use cases, right? Which is what kind of solutions we can build. Like you look at agent frameworks, what they can do, RAG, structured information in the third session, and look at the case studies of real world case studies of customers was implemented, what is the problem statement they had, what challenges they faced, how did they build a model, what worked and what did not work, right? And then finally, we'll also look at the important aspect like model alignment. So AI is an ethics also, which is an essential part to learn nowadays. So that brings us to the end of today's session. I will share the video. So let me stop recording in the meantime.